Welcome back. Today we will see anatomy of MapReduce. So, as we have seen earlier, what a MapReduce is, the two tasks which is very crucial in Hadoop. The MapReduce takes input from the input tools. It processes the data and generates the exact output needed for this task. Now we'll see what exactly anatomy of a MapReduce. That is how MapReduce task works in the background. Input data is split into small subsets of data. Map task works on these data splits. This the intermediate data input data from map task is submitted to reduce task after an intermediate process called shuffle. The reduce task works on this intermediate data to generate the result of a MapReduce job. So this is the internal anatomy of a MapReduce task that is carried out in Hadoop. Now we will see one by one what exactly this anatomy works. Right. So let's see graphically. So this is a diagram where it shows how the data is being input to Hadoop system and how different map and reduce task will process the data. Now we'll see one by one. So in this example, we have two nodes, node 1 and node 2. The data from the input system will be distributed to nodes available in the cluster. So as per this example, we have two nodes, node 1 and node 2. So the data will be distributed among these two nodes. Once the data has been distributed to the nodes, next the task will be carried out to the map task. So each map task works on a split of data. That is, whatever the data that has been come from the node 1 will be transferred to the number of maps in the cluster. So as for this example, we have two nodes, node 1 and node 2. So the data is being distributed to these nodes, and now each map task will be started execution on the input data. Now the mapper outputs intermediate data after processing the input data. So this is where the map task output is being generated. Now in between the data transfer to map and reduce, there is an important process called as shuffle. So the data that is generated from the map will be transferred to the reduce phase after shuffling process has been completed. So in the next coming slides, we will see what exactly the shuffle process is, but as of now we will see how the data will be passed. Now the data that has been coming after shuffling will be transferred to the reducer. So as number of nodes, we will see the number of reducers here. So intermediate data of the same key goes to the same reducer. So based on the keys generated from the mapper and after shuffle process, the data will be transferred to the reduce. Okay. Now once the reduce gets input, it processes the data, it generates the required output, and the output will be stored in the same node where it has been processed. That is, for example, reduce 1 has generated data, and the data output data will be stored in node 1, whereas reduce 2 which generates data will be stored in the node 2. So this is how the entire process of MapReduce task at a glance. Now we'll see one by one. Now we'll see. It's a detailed diagram and what are all the phases that will be carried out while a MapReduce task works. Now we'll see. So we need to remember one thing, that in a MapReduce task we often talk about intermediate key value pair. So that key value pair is the exact output that we receive after the MapReduce task has been completed. Now see, input data that has been stored in HDFS, that's a Hadoop distributed file system. So once the data is there, we select input format that need to be supplied to the MapReduce task. So once the data is there, we'll split the data into n number of input splits based on the availability data and based on the available nodes. Now, once the input split has been generated, the input split will be passed through number of record readers that are available in the cluster. So, once the record has been registered in the record reader, the input will be transferred to mapper. So, the n number of mappers based on the n number of nodes in the cluster. Once the data has been moved from mapper and it performs its required operations, the data will be passed to the next stage called as combiner. So, similarly, all the other mappers will also generate outputs and the data will be passed to the combiner. After that, the data will be transferred to the partitioner, which performs some partitions on the data, and once the data is been partitioned, all the data will be passed through shuffling and sorting phase. So this is the place where the data shuffling and sorting will be done based on the intermediate key value pairs. Right. So here, as seen, input key value pair generated from mapper. Here, a substitute intermediate key value pair will be generated after the combiner phase. So all this data will be traveled to shuffling and sorting phase. Once the data has been shuffled and sorted, the output data will be passed to the number of reducers, and each as per the mapping, the data will be moved to the exact reducer. Okay, once the data has been received by the reducer, they perform the required operation and they generate the output format from the given input. So once the data receives and after the reducer process, the data will be stored onto HDFS system. This is how a complete transition from input to output takes place in the MapReduce task. Now we'll see what are all the terminologies we undergo in this MapReduce task. So first one is the input files. So the data that is to be processed by the MapReduce task is stored in the input files. So whatever data we need to process, that will be stored in these input files. These input files are stored in Hadoop distributed file system. That is, the data will be stored in HDFS. Shortly we'll call it as HDFS. This data will be available in the HDFS system. The file format is arbitrary, while the line based log files and the binary format can also be used. So the files, two types of files can be used here, log files and the binary format files. Next thing is input format. It specifies the input specification for the job. So it depends on the type of job that we are supplying to the MapReduce. So input format validates the MapReduce job input specification and splits up the input files into logical input split instances. So that is, the large volumes of data will be split into number of splits based on the criteria. These are called as input split instances. Each input in split is then assigned to the individual mapper. So as we have seen in the diagram earlier, each and every mapper will have some input from the system. That's the input splits. So that input split will be assigned to individual mapper after the data has been performed into splits. Now text input format is the default input format for the mapper. Now next one is a input split. It represents the data for processing by the individual mapper. So whatever number of mappers we have, the input split represents the data that is required for the individual mapper. Input split typically presents the byte oriented view of the input. So that is, the data seen by mapper here will be in a byte oriented view. Right. So now it is a record reader. So we have seen the record reader in the earlier diagram, which its responsibility is to process and present the record oriented view for the mapper. So the default input split is the file split. The files which are split into number of pieces will be represented here. Now record reader. So record reader reads the key comma value pair. So this is very important. Whenever we talk about MapReduce task, the input data and output data will be in this format only, the key and the value. So record reader reads the key comma value pairs from the input split. So input split will contain this key comma value data. It converts a byte-oriented view of the input and presents a record-oriented view to the mapper implementations for processing. So record reader will give as a record-oriented view to the mapper which needs to be processed. Now it is responsible for processing the record boundaries and presenting the map task with keys and its values. So the record reader breaks the data into key comma value pairs for input to the mapper. So this is where the mapper gets this key comma value pairs as an input to process on it. Next one is mapper. The mapper maps the input pairs to a set of intermediate value pairs. It processes the input records from the record reader and generates the new key comma value pairs. Right. So once the mapper receives the data from the record reader in a key comma value pair, it again generates its new key comma value pairs after its processing. So the key comma value pair generated by mapper are different from the input key comma value pairs. So the input received from record reader will contain key comma value pairs, but once the mapper performs the processing on the data, it also generates its own key comma value pairs. So both the key value pairs will be different to each other. Next, the generated key comma value pairs is the output of mapper known as intermediate output. So in the MapReduce task, when we give input, the first data, as we know, processed by the mapper. So once mapper processes the data, it generates its output, and its output is called as intermediate output. And these intermediate outputs of the mappers are written to the local disk. So we are directly writing it to the local node. That is where exactly the mapper has executed its output. We are not storing directly to Hadoop. The mapper's output is not stored in the Hadoop distributed file system because as the output generated by mapper is a temporary data, and writing this data on HDFS will create unnecessary copies. So if you copy the data which is intermediate output to the HDFS, it unnecessarily occupies the disk space and also makes redundant copies of the data. So that is of no use. So the output of the mappers is then passed to the combiner for further processing. So as the data which is stored in the local disk will be passed to the combiner for further processing. Now we'll see what combiner does. Combine is also called as a mini reducer. The combiner performs logical aggregation on the output of the mappers. So mappers generated output will be passed to combiner, which performs local aggregation on the data. This helps in minimizing data transfer between the mapper and the reducer. After the execution of the combiner function, the output is passed to the partitioner for further processing. Now what the partitioner does here? When we are working on the MapReduce program with more than only one reducer, then only the partitioner comes into the picture. So that is, if we have multiple nodes and we have more number of reducers, then only the partitioner comes into action. If we have only one reducer, we do not use any partitioner. So it depends on the number of reducers we have in the cluster. It partitions the key space. It controls the partitioning of keys of the mapper intermediate outputs. Again, partitioner takes the output from the combiner and performs partitioning. Key is for deriving the partition typically through the hash function. So we define some hash function, and based on that hash function, it derives a partition. The number of partitions is similar to the number of reduced tasks. So hash partitioner is the default partitioner that we use in MapReduce program. So it partitions into the number of reduced tasks based on the count. That is, if you have 5 reduced tasks in your cluster, then the partitions will be 5. So for that purpose, we use hash partitioner as a default partitioner in the Hadoop system. And the next phase is shuffling and sorting. The input to the reducer is always the sorted intermediate output of the mappers. So that is, output generated by mapper will be sorted in an order, and that order will be given to the reducer as input. So it's a mandatory that always sorted data shall be given to the reducer. After combining and partitioning, the framework via HTTP fetches all the relevant partitions to the output of all the mappers. Once the output of all the mappers is shuffled, the framework groups the reducer inputs on the basis of the keys. So based on the input keys, it sorts the data. This is then provided as an input to the reducer. Right. Now the reducer comes into action. The reducer then reduces the set of intermediate values who shares a key to the smaller set of values. The output of reducer is the final output. So this output is stored in the Hadoop distributed file system. That is, we have seen mapper output data will be stored into local disk, but the output generated by the reducer will be directly stored to the distributed file system because it is the final output of the application or the job that you have given as input. Now next thing is record writer. Record writer writes the output in the form of key comma value pairs of reducer to an output file. It writes the MapReduce job outputs to the file system. This is where exactly the user can see their output, and it depends on the output format. The output format specifies the way in which these output key comma value pairs are written to the output files. It validates the output specification for a MapReduce job. That is, what is the specification that has been given before the job has been assigned to the MapReducer, that will be validated with the output generated by the reducer. Output form basically provides the record writer implementation used for writing the output files of the MapReduce job. The output files are stored in a file system. Hence, in this manner, MapReduce works over the Hadoop cluster in different phases. So this is the anatomy of MapReduce up to set extent. Now we'll see what are the important components in which a MapReduce can be broken. It is called as anatomy of a MapReduce. We'll see the three main components. Among that, first one is a map function. The map function is responsible for processing the input data and producing intermediate key comma value pairs. The map function takes an input key comma value pair and produces 0 or more intermediate key value pairs. So in certain cases, if there is no accurate data or proper data, it may generate 0 key value pairs, but it will be very rare. But where more intermediate key value pairs will be generated after the mapper phase has been executed. The map function is executed in parallel on different nodes in the cluster. That is based on the number of nodes we have in the cluster, all the mappers will work in parallel. Right. That is a map function. Now we'll see shuffle and sort. As we known earlier, the important phase in the MapReduce job is shuffle and sort phase. The shuffle and sort phase is responsible for sorting the intermediate key comma value pairs and partitioning them according to the keys. So based on the keys, the intermediate key value pairs will be sorted in the system. This phase ensures that all intermediate key value pairs with the same key are set to the same reduce function. This phase is executed on the master node. Okay. This is the phase of shuffle and sort. And another important one is reduce function. The reduce function is responsible for combining the intermediate key comma value pairs and producing the final output. The reduce function takes an intermediate key and a list of values and produces 0 or more output key value pairs. If there is no exact key matching or exact data, then it may also generate 0 outputs. But in many cases, it generates key value pairs based on the given input. The reduce function is executed in parallel on different nodes in the cluster. So as mapper performs parallel processing in the cluster, the reducer function also gets executed parallelly on the different nodes available in the cluster. Now, there are some intermediate jobs that are being running in the MapReduce task. Now we will see them one by one. First one is the job run. A job run involves the execution of a MapReduce program on a set of input data to produce an output result. The job run process can be broken down into several steps. So that is, the job run task is mainly to involve the execution of MapReduce program based on the input data supplied to the program. We'll see the steps here. Input data splitting, map task execution, intermediate data shuffling, reduce task execution, output data writing. So these are already discussed, but we'll see internally what exactly each phase will perform. First one is the input data splitting. So the input data is divided into small chunks called as input splits. Each input split is processed by a single map task. So that is, the data will be splitted into small chunks which are called as input splits, and these input splits will be supplied to each and every map task. That is, one map task will work on one input split. Now, map task execution. So job run's another responsibility is to take care of the map task execution. So the map task processes the input split and produces a set of intermediate key comma value pairs. The map task is executed in parallel on different nodes in the cluster. Now, intermediate data shuffling. The intermediate key value pairs produced by map tasks are sorted and partitioned by key. So based on a key, the value will be shuffled. This ensures that all intermediate key value pairs with the same key are sent to the same reduce task. That is, whatever the data that are mapped with the key will be passed as an input to one single reducer. So based on number of keys, we'll select the number of reducers. So now, reduce task execution. The reduce task takes the intermediate key value pairs with the same key that has been defined here and produce the set of output key value pairs. The reduce task is executed in parallel on different nodes in the cluster, same as with the mapper. Now, task is output data writing. Once the output is generated from the reducer, the output key value pairs produced by the reduce task are written into the output file. The job run process in managed by a job tracker in Hadoop. So as we know, we are talking about Hadoop. The job run is called as job tracker in Hadoop system, or a resource manager in Yarn. If you are using Yarn as a job manager, then you will use resource manager, which takes care of the job run process. The job tracker or resource manager is responsible for assigning map and reduce tasks to available nodes in the cluster, monitoring the progress of job and handling any failures that may occur during the MapReduce task. So this is as we know, we have two types of job run process here. One is the job tracker and the second one is a resource manager. Both are responsible for assigning the task to map and reduce tasks and monitor the progress of the job, and if any failure occurs, that has to handle the failures. That is, assigning the job to another map or reducer based on which has been failed in the system. Now, what could be the list of failures that may occur in MapReduce? So these are the hardware failures, software failures, network, input data issues, and resource allocation issues. These are the possible failures that may occur in MapReduce job. Now we'll see what exactly each type of failure is. Hardware failure. Nodes in the cluster can fail due to various hardware issues such as hard disk crashes, power supply failures, network connectivity issues, etc. These failures can cause the loss of data or processing power and can slow down the entire MapReduce job. That's a physical hardware issues are termed under hardware failures. That is a hard disk crashes or power supply failures or network connectivity issues. They may be termed as hardware failures, and if any of these failures occur, it will be causing the loss of data or processing power, and that may slow down the entire MapReduce job. The next one is software failures. The MapReduce jobs rely on various software components such as Hadoop, Yarn, MapReduce framework, etc. So these are various softwares that are available in the system. If any of these software components fail or experience some bugs, then the entire job can fail or produce incorrect results. So software failures may generate data even though it has failures, but the data may not be exact data that you are expected. So this is a one kind of failure, software failure. And the next one is network failure. MapReduce jobs require a stable network connection between the nodes in the cluster. So there is a in the MapReduce phase, the data will be transferred from one node to another node that are available in the cluster based on the data that has been stored in the system. So in this scenario, if there occurs any network issues such as congestion or packet loss or connection drops, then it can cause delay of data transfer between the nodes in the cluster, and sometimes it may even cause failure of the job in the system. So this is one kind of failure called as network failure. And the next issue is input data issues. There's a input data to MapReduce jobs can also cause failures if the data is corrupted. That is, if the input data you have to be supplied to the MapReduce job is having some issues, some data is corrupted, then the MapReduce may generate incomplete or data in a wrong format. In such cases, the job may fail to process the data, or sometimes it may produce incorrect results. Now, the last one is resource allocation issues. MapReduce jobs require resources such as system memory, CPU cycles, and also disk space to store the data intermediately. If these resources are not properly allocated, or if you have any shortage of the resources, then the job may fail or produce incorrect results. Even if you have less resources or shortage of resources, the job also may get delayed in execution. So these are some failures that may occur in the MapReduce job. Now we'll see what exactly shuffle and sort intermediately performs on the data. The shuffle and sort are important phases in the MapReduce framework that occur between the map and reduce phases. The shuffle and sort will be performing its action in the between of map and reduce jobs. They are responsible for grouping and sorting the output of data from the map phase before it is passed to the reduce phase or for processing. So in between map and reduce, we'll have the shuffle and sort process. Now first see what's a shuffle phase. The process of transferring data from the map phase to the reduce phase will be carried in the shuffle phase. During the shuffle phase, the map output data is partitioned and sent to the reducers. The map output is grouped by keys, and each group of data with the same key is sent to the same reducer. So this will help the reducer to perform faster processing on the data without waiting for another reducer to give the required data. The partitioner is responsible for deciding which reducer each key value pair will be sent to based on the key that is available in the mapper output. Now sort phase. The sort phase is a process of sorting the map output data within each reducer. The map output data is sorted by key before it is passed to the reducer. The sort phase ensures that all the data with the same key is sent to the reducer in a sorted order. This makes it easier for the reducer to process the data efficiently and also perform faster processing on the given input data. Now map plus task execution. A MapReduce job usually splits the input data set into independent chunks which are processed by the map task in a completely parallel manner. So that is, as discussed, the data will be split into number of input splits, which may be called as independent chunks, which will be given to each and every map task in the cluster that needs to perform in a parallel manner. The framework sorts the outputs of the maps which are then input to the reducer task. So in that framework we have seen shuffle and sort system. The next thing is typically both the input and output of the job are stored in a file system. So that depends. If a mapper stores the data into local disk, but whereas reducer stores the data into HDFS. So both are different file systems where the data will be stored. So this is an anatomy diagram which we can see to understand how exactly the MapReduce program works. We'll see in detail here. So the first one is a MapReduce program that is responsible to perform processing on the input data. So first step is run job. And I have seen yarn or job tracker which takes responsibility of running the job of MapReduce program. So first run job is the module where exactly the job is available. So first step run job, and second step it gets application from the resource manager. So for running a job we need application, and that will be available with the resource manager. So now the client node requests for getting a new application. Once it has been given by the resource manager, the job again contacts the shared file system where the resources are available. Now in this phase, third step, it copies the job resources from the HDFS. Once it has been copied, now after taking that job resources, it again submits application to the resource manager for further processing. That is, it will now allocate resources to the job. So as the next step, fifth step, the resource manager starts a container specific to the particular job that has been requested. So now one task needs some resources. That resources will be given as a separate container for each and every job. Now the node manager, intermediate node manager, will launch the job for that particular job. So now once it will launch, the job will get initialized in the MR app master. That's a MapReduce app master. Here the jobs gets initialized. When the job gets initialized, the acquired data need to be fetched from the shared file system or the HDFS system. So what it does here in this phase, it retrieve input splits that has been splitted into number of splits. Once the data has been received from here, input splits, now the next task is to get exact resource allocation. Now we have the data based on the number of input splits. For example, if you have 10 input splits, then you need 10 mappers. That will be again requested with the resource manager. Now the resource manager assigns the resources, and the next step is to start a separate container for that particular job. Now again the node manager that runs on the node manager will launch the exact output. Now this makes the mapper to get into picture. Now here, this in the example we have seen yarn child. This is another job tracker which takes care of the entire MapReduce task. Now once it has been launched, it will retrieve the job sources again from HDFS and then performs the exact task. Now in this phase, we will first go with map task, where it generates the intermediate key comma value pairs and stores it in the local disk. Once it has been done, the data will be passed to shuffle and sort phase, and the shuffle and sort phase performs its operation and sorts the output that has been received from mapper based on a key. Now based on the key, the same key value will be passed to reducer. So based on the available number of keys, the number of reduce tasks will be defined, and these reduce tasks perform the exact data and generates the output that will be stored into the HDFS. So this is how the MapReduce task follows different phases and performs the execution of the given input data. So there are some independent entities that we undergo in the MapReduce task. See, the client which submits the MapReduce job, the yarn resource manager which coordinates the allocation of compute resources on the cluster, the yarn node manager which launch and monitor the compute containers on machines in the cluster, the MapReduce application master, MRApp master, which coordinates the task running the MapReduce job. The application master and the MapReduce task run in containers that are scheduled by the resource manager and managed by the node managers. And next one is the distributed file system, which is used for sharing job files between these available other entities. The job submission. The submit method on job creates an internal job submitter instance and calls the submit job internal on it. Having submitted the job, wait for completion, polls the job's progress once per second and reports the progress to the console if it has changed since the last report. When the job completes successfully, the job counters are displayed. Otherwise, the error that caused the job to fail is logged onto the console. The job submission process implemented by job submitter does the following in background. It asks the resource manager for a new application ID used for the MapReduce job ID. It checks the output specification of the job. For example, if the output directory has not been specified or it already exists, the job is not submitted and an error is thrown to the MapReduce program. Now, then it computes the input splits that has been divided for the job. If the splits cannot be computed because the input spot does not exist, for example, the job is not submitted and an error known as thrown to the MapReduce program. So if the input path that has been specified does not exist, it will throw an error to the MapReduce program. It copies the resources needed to run the job, including the job jar file, if you are using Java system, the configuration file and the computed input splits to the shared file system in a directory named after the job ID. So based on the job ID that has been generated here, the folder is generated and all the required resources like input splits, configuration file and jar file, these are combinedly stored in this shared directory. Once it is done, it submits the job by calling submit application on the resource manager. So once it is allocated, now it is a initialization phase. When the resource manager receives a call to its submit application method, it hands off the request to the yarn scheduler. The scheduler allocates a container and the resource manager then launches the application master's process there under the node manager's management. Now, the application master for MapReduce job is a Java application whose main class is a MRApp master that we have seen in the anatomy diagram. It initializes the job by creating a number of bookkeeping objects to keep track of the job's progress, as it will receive progress and completion reports from the task. Now, it receives the input splits computed in the client from the shared file system. Once it is retrieved the input splits, then it creates a map task object for each and every split received, as well as a number of reduced task objects determined by the MapReduce.job reduces property that is set by set number reduce task methods. So it defines how many number of reduced tasks you need after the mapper generates the output. The task assignment. If the job does not qualify for running as an Uber task, then the application master requires containers for all the map and reduce tasks in a job from the resource manager. Now requests for map tasks are made first and with a higher priority than those for reduced tasks, since all the map tasks must complete before the sort phase of the reduce can start. So before starting the reduce phase, all the map tasks should complete its output and give it to the shuffle and sort phase. So once it has been received the sort phase, then it will be transferred to the reducer. Requests for reduced tasks are not made until 5% of map tasks have completed. So once the at least 5% of map tasks is completed, then it will start requesting the number of available reduced tasks to perform sort, shuffle and sort phase. Now task execution. Once a task has been assigned resources for a container on a particular node by the resource manager scheduler, the application master starts the container by contacting the node manager. So after contacting the node manager, then only it starts the application master, which takes the data from the container. The task is executed by a Java application whose main class is your_child. Before it can run the task, it localizes the resources that the task needs, including the job configuration, jar file, and any files in the distributed cache. Once all the resources are available, then it runs the map or reduce task based on the phase. Now the data streaming. How the data streams here? See, we have node manager and the task JVM, map task or reduce task, and streaming process. Streaming runs special map and reduce tasks for the purpose of launching the user separate executable and communicating with it. The streaming task communicates with the process, which may be written in any language using standard input and output streams. During execution of the task, the Java process passes input key values as input to the external process, which runs it through the user-defined map or reduce function and passes the output key value pairs back to the Java process. So this is how it takes input, performs operation, and generates output. From the node manager's point of view, it is as if the child process ran the map or reduce code itself. Now, job completion. When the application master receives a notification that the last task for a job is complete, it changes the status for the job to be successful. So once everything has been executed, it is into successful stage. Then when the job polls for status, it learns that the job has completed successfully. So it prints a message to tell the user and then returns from the wait for completion. So wait for completion status gives that the job has been run successfully. Finally, on job completion, the application master and the task container keyed up their working state and the output committers commit job method is called. Job information is archived by the job history server to enable later interrogation by users if they desire it. So MapReduce types there. So MapReduce is a programming model used for processing large data sets in a distributed environment. In this model, data is divided into smaller chunks and processed in parallel across multiple computing nodes that are available in the specific cluster. There are three types of MapReduce. We have traditional MapReduce, streaming MapReduce, and incremental MapReduce. Traditional MapReduce. This is the original form of MapReduce developed by Google. It consists of two main phases: the map phase, where data is divided into smaller chunks and processed in parallel across multiple computing nodes, and the reduce phase, where the results of the map phase are combined to produce the final output. So this is the traditional MapReduce that has been developed by the Google. Second one is streaming MapReduce. This type of MapReduce allows data to be processed in real time rather than in batches. So it simply avoids the batch processing of the data. Data is fed into the system as a stream, and each record is processed as it arrives. So as the data starts arriving, the phase starts executing the arrived data. This makes it suitable for applications such as log processing and real-time analytics, because in batch processing we need to wait for the data. Once all the batch data is received, then only we can perform operation on it. But for applications such as log processing and real-time analytics, the data need to be given as a stream of continuous data. Next one is incremental MapReduce. This type of MapReduce is used for iterative processing. So if you need to perform processing the data iteratively, then this MapReduce will help us, where the same data set is processed multiple times with different parameters. So that is iterative processing will have the same data that need to be processed multiple times. Each and every time it may vary with the parameters given to it. Instead of processing the entire data set for each iteration, only the changed or updated data is processed. So this will help both the execution time, less time and less storage can be utilized in this process. This makes it suitable for applications such as machine learning, where model needs to be trained iteratively on large data sets. So this is one type of example application for incremental map reduce. Now what are the types of input formats that we can supply to a map reduce job? So text input format, sequence file input format, Hadoop archives input format, DB format and combined file input format. So text input format. This is the default input format for MapReduce. It reads plain text files and splits them into separate records. Each record is a line of text and the key is the byte offset of the line in the input file. So this is the first type of input file. Next one is a sequence file input format. This input format reads binary key comma value pairs stored in a sequence file format. Sequence files are often used as intermediate format in Hadoop workflows. Hadoop archives format. This input format reads data stored in a Hadoop archive file. Hadoop archives are used to combine small files into a single compressed file for more efficient processing. So this is a HAR archive files. Next one is DB input format. This input format reads data from a relational database using JDBC. So as we know, Hadoop runs mostly on Java. It uses JDBC as a database. It allows MapReduce jobs to process data stored in a database table. So the input will be retrieved from a table or a database system to the MapReduce job. A combined file input format. This input format reads multiple small files and combines them into a single split. This can improve performance by reducing the number of input splits that processed by a MapReduce job. And there are different output formats. So different output formats we have here are text output format, sequence file output format, multiple outputs, Avro output format, Parquet output format, sequence file as binary output format and DB output format. So let's see one by one. Text output format. This is the default output format in MapReduce. It writes the output as plain text files where each line represents a key value pair separated by a tab or a delimiter of your choice. That's a user choice. You can use any of the delimiter. Next, sequence file output format. This output format writes the output as binary files called sequence files. Sequence files are compressed and splittable, making them suitable for storing large amounts of data efficiently. Next one is multiple outputs. This allows you to generate multiple output files from a single MapReduce job. You can specify different output formats for each named output, enabling you to write different types of output files based on your requirement. Next one is the Avro output format. This output format writes the output in Avro format, a compact binary data serialization system. Avro files are self-describing, meaning that the schema is stored along with the data, making it easier to work with structured data. Next one, Parquet output format. This format writes the output in the Parquet column storage format, which is optimized for big data workloads. Parquet files are highly compressed and support efficient columnar operations, making them suitable for analytics and querying. As we know, analytics needs columnar data. This Parquet output format generates the data in Parquet files. So these are some comparisons. Feature row-oriented storage and column-oriented storage. That's a Parquet one. Storage efficiency. As in the row-oriented storage, it is good for OLTP, online transaction processing, workloads where individual rows are frequently accessed. But for it is columnar storage is better for OLAP works where analytical queries typically access a subset of columns. So for analytics processing, this helps a lot. A compression. It's limited by data locality within rows, making it less efficient for compression, but more efficient compression due to similar data types being stored together within the columns. Query performance. Query performance can degrade as the number of columns accessed in a query increases. But whereas in column storage, query performance remains stable even only a subset of columns is accessed. Schema evolution. Schema changes can be complex and may require modifications to existing data and applications. But in column storage, it supports schema evolution without breaking compatibility, allowing for easy addition or modification of columns. Integration. Widely supported in relational databases and traditional data warehouses. Column storage is seamless integration with Apache Hadoop ecosystem tools like Hive, Spark, and additional tools. Next, sequence file as output format. It is similar to sequence file output format. This format writes the output as binary sequence files but treats the key value pairs as a binary data rather than serialized objects. The last one is a DB output format. This output format allows you to write the output directly to a relational database. It provides a convenient way to load the results of a MapReduce job into a database table. So this will be the example of general web applications where the data is fetched to the application through relational database and the output is stored again into relational database. So this is the exact format which is similar to web applications. So this is a complete picture on anatomy of a MapReduce job. Thank you.